What we're trying to do with this chamber is mimic the type of conditions that you have inside a running, working engine.
A Sandia National Laboratories LED driver is generating light pulses with shorter duration, higher repetition frequency, and higher brightness than anything on the market. A powerful new tool for illuminating extremely fast processes such as fuel injection.
The only reason that we can see this fine detail, this fine structure, is because the short duration of the lighting.
Being able to use light in this way is allowing us to see things that we couldn't see before.
I don't think we can go anywhere and find a $600 light that could replace a laser and that could do short pulses at high frequencies. This is enabling specific experiments that nobody else can do.
The Sandia LED Pulser uses custom electronic circuitry to drive high-power LEDs to generate short, bright, high-frequency light pulses. A single device can emit up to 4 different colors, each with independent pulse timing, crucial for light beam forming in many optical applications. The technology was inspired by the wide variety of LED products, and key is understanding the electronics when pairing different LEDs and driver components.
Characteristics that are important is impedance, capacitance of the full board. Running at nanosecond pulses at megahertz frequencies is something that requires all these parameters to be under control in the real way. Last year is the first time that we actually reached pulses that were below 10 nanoseconds. And actually, the driver is part of it, but the LED from the manufacturers is also another one. But most importantly, it's actually the coupling of both and the understanding that one LED package would have a certain behavior, certain characteristics, and use these characteristics to our best advantage with the drivers we've been designing here at Sandia. And so coupling these two enabled to reach very, very short pulse durations.
At Sandia's Engine Combustion Department, researchers strive to help automakers design vehicles with lower emissions and more efficient engines. Fast, high-resolution digital imaging inside the chamber provides the type of data needed to develop advanced computer models that predict precisely what will happen.
So once we have the conditions right, we would inject a fuel spray into that environment, and now we can watch how the fuel and air mix together.
Critical to image capture are light and optics, and the LED Pulser provides many advantages over expensive laser systems.
What we're replacing it with is a device that's much, much smaller, much more efficient in terms of power, and much more versatile. So we can, rather than having to direct the laser beams around through optics, we can basically set this up as it's needed to do the kinds of illumination that we want in the engine.
Every single pulse is more or less identical to the other one, and this is true throughout millions of images. And every time I start this, it doesn't need heat up, it doesn't need warm up, it's ready to go from the start. So no laser can do this.
Ongoing work requires fast diagnostics to accurately model and understand how fuel spray mixes with surrounding gases. Here the team couples the LED Pulsar to a high-speed camera to achieve nearly 200,000 pictures per second.
The shock waves move out across the combustion chamber, hits the back wall, and it's actually reflected and comes back and reaches the spray. And this diagnostic is a Schlerin diagnostic. It's sensitive to a gradient in density, and so we can see not only where the shock wave is, but we can see the boundary of the fuel vapor in one of the plumes of the fuel spray. And this type of information, the rate that it penetrates out across the chamber, the way that it mixes, its boundary, is one of those critical elements that is needed in order to make the computational tools better.
So like having a ring of LEDs that's actually cool.
Beyond combustion optimization, researchers are working with even shorter pulses for use with high-speed, long-distance microscopy. And there are potential applications in the manufacturing and medical sectors as well. It's a novel approach to illumination leading to new scientific discoveries.